Okay, so in terms of this lab is a whole bunch of different ways to look at Newton's three laws of motion. First one is law of inertia. Basically says, hey, whatever velocity vector an object has is whichever one it wants to keep. Now sometimes you see it says an object at rest remains at rest, or an object in motion remains in motion until an outside force acts upon it. Now, the part about the force is that that force can do one of three things to a velocity vector. It can make the velocity vector bigger, it can make the velocity vector smaller, it can change the direction of that velocity vector. Okay? So none of which today are going to be talking about circles. So if I give this apple a push, okay, the only reason that this thing comes to a stop, the only reason any of you come to a stop, isn't because that's the preferred state of motion. It only comes to a stop because there is friction. If you eliminate friction, it will just keep going. It will maintain whatever velocity that you have. And so that's what happens when you launch something out into like space, okay? So once you fire something out into space, you don't have to keep applying a force to it because there's no opposing force. So once you get an object moving in space, you can shut off the engines because then it's just going to keep maintaining whatever state of motion that it has. So whenever you keep applying a force to keep something moving, that force is only there because there is an opposing force, okay? We'll talk more about this later, but a lot of times we'll refer to like we're going to have two types of mafia. We're going to have the frictional mafia, we're going to have the gravity mafia, okay? So today you guys are going to be dealing with the gravity mafia in terms of what you're going to be pushing. So it's like you're trying to push this block along, and the frictional mafia goes, "Hey, you're a good boy. You want to push the block? You got to give us some tribute, okay? You got to do this. You're a good boy, okay?" So basically, that's what the frictional mafia does. It says, "Hey, you got to pay us to move through our territory." And the question is how much money do you have to pay? So when you guys were pulling this, and I emphasized the two words at a constant velocity. So when you guys got through Friday, like you pulled that block, and let's say it took you, I don't know, 1.20 newtons to pull it, whatever your force was. So the only reason that that applied force is there is because there's a frictional force of negative 1.20 newtons. Okay? That's it. Now, everybody says, oh, this is Newton's third law. This says for every action there is a reaction. This is not Newton's third law. Newton's third law occurs when you have an action-reaction force in a pair. So like if this is literally it is a 1 Newton apple. So what happens is like if I hold up this apple, I'm exerting an upward force of 1 Newton. The Newton, or the apple, is exerting a downward force of 1 Newton, okay? I drop it. The earth is exerting a downward force on the apple. The apple is exerting an upward force on the opposite direction, okay? So typically when you have action-reaction forces, typically they are in contact. So when I push down on my hand, when I slap at the table, I exert a downward force on the table. By Newton's third law, not Newton's suggestions, not Newton's, well, maybe, only on test days. These are laws. So if I push down with negative 5 newtons, the table has to push back with the force of positive 5 newtons, okay? No exceptions to this rule. None, zero, zip, none, stop, stop, okay? So when you pull on the block, okay, with the spring, that's an action-reaction. You're pulling on that hook, and the hook is pulling back on you. This frictional force is just there because that's how much force that has to be overcome to make this thing move. So you're going to calculate mu, and you're going to take force friction over force normal. So one way to calculate or determine that force friction is measure how much force it takes to make something move at a constant velocity. That's option number 1. Divide that by your force normal. Remember, technically force normal is Fg cosine theta. For now, we're not going to worry about the cosine theta part. remember this is also an absolute value. So none of your mu's should be negative, and they should be typically in the 0.2 to about 0.8 range, okay? If you ever get a mu of like 4, something's gone horribly wrong, okay? Rare that it even gets above 1. Okay, so what you're gonna do on the next part, you're gonna take your block, and then you're gonna take a 100-gram mass, and you're gonna stack that on top of that, okay? And then you're gonna measure how much force it takes to pull it at a constant velocity. Now, you need the total weight of the system. You're gonna know the weight of the block. How are you gonna find the weight of the block? Yeah, hold it up, boom, there you go. 3.85 newtons, whatever that is, okay? Whatever that is. Now, the 100-gram mass, since you know specifically what that mass is, how can you find the weight of a 100-gram mass?
Convert to newtons.
Well, 100 grams is how many kilograms?
0.1.
0.1 kilograms, right? Divided by 1,000. I take 0.1 times 9.8 meters per second squared, I get 0.98 newtons. So what you want to do, where it says that force normal, okay, actually you're going to do 200, not 100, you're going to do 200. You're going to take 0.2 times 9.8, and you're going to get 1.96 newtons. So you're going to take 1.96 plus the weight of the block. Then you're going to take 0.5 kilograms, multiply that by 9.8, add that to the weight of the block. And you're just going to keep pulling this. So this is going to be a graph that you're going to draw, okay? And I tell you, you're going to put your force friction here and your force normal here, okay? Should get a pretty decent shaped graph. Okay, let me back up one. I went step one. I forgot I didn't cover this on Friday. So underneath your chart, on number 1, I want you to understand exactly what I want on number 1. You're going to draw a free body diagram labeled all the vectors. So on number 1, on another sheet of paper, you're going to choose a scale. So your forces are probably pretty small. Like Keaton, what was your force to pull it at a constant velocity on that wood on wood?
Wood on wood?
Yeah.
1.45.
Okay, so if you let 1 centimeter equal a newton, you're going to have this little vector that's about yay long. So what I would recommend is that you might let 2 centimeters equal 1 newton. That's going to make the vectors a little bit bigger, okay? And it's going to make it easier for you to draw them. And more importantly, it's going to make it easier for me to see them. So when you get done, you're going to say whatever scale you're going to choose. You're going to draw this with a ruler, okay, to scale. And you're going to go, oh, here's my FG, here's my normal, here's my applied, here's my force friction, okay? You want to think of the mafia, I don't care. So you're going to draw these, put what they are and that value. This would be like negative 3.85, whatever yours is, okay? Then label these. So that's what the first diagram is going to be. The second diagram, you're going to draw them in a tip-to-tail method. Personally, I always draw my gravitational force first, okay? That's just the one that I always draw. So then I'm going to go, well, I got this force applied. I've got my normal force. I got my force friction, okay? So a plus sign is what the first one's going to look like. A rectangle is what the second one is going to look like, okay? And again, these are the wood on wood, constant velocity. So this is diagram number 1, diagram number 2. Then you're going to have a graph off that data on part 2 with the kinetic friction with different weights. So you're going to have force friction here, and you can have force normal here. You can have some points, boom, draw that line. And pay attention that I tell you that circle the points and write the coordinates on the graph. You have to pick points that are on the line of best fit. That's the whole point of drawing a line of best fit, okay? Don't pick points that aren't on the graph or aren't on the line of best fit. Okay, now, let's talk about another way you can deal with forces. Any force can also be written as mass times acceleration, okay? So let's say that you have a carrot car that's moving at 10 meters per second. Bam, we hit the brakes. We end up stopped. And let's say that that took 2 seconds, okay? Where you're driving along dry pavement, 10 meters per second, bam, you slam on the brakes, stops in 2 seconds. Did the car accelerate?
Yes.
Yes. So you had a certain velocity vector, and that velocity vector became smaller, right? So some force had to act on the car. Because if a force did not act on the car, it would keep moving at 10 meters per second. So assuming that when you hit the brakes that there was friction, friction was what's going to make this car slow down, right? So this, if you can find your acceleration, well, that's easy. Oh, that's going to be 0 minus 10 meters per second divided by 2 seconds. Now I'm going to get negative 5 meters per second squared. So if the mass of the cart is, make the math easy, 10 kilograms, whatever that is. So the other way that you can calculate your force friction is take mass and multiply it by the acceleration that was caused by friction. So if I take this book, right, and push it, oh, if I know my initial velocity, I know my final velocity is 0. Either I know my distance or I know my time, I can calculate the acceleration. Once I know the acceleration, I can multiply that by the mass. So that's the second one. So the first way you can determine your force friction, how much force does it take to pull it? The second one you can do is mass times acceleration. Okay? So if you know what the mass of the car is and you know the acceleration caused by friction, you can just use MA. Now the third way is that you know mu equals force friction over force normal. So if you know what mu is, like let's say for example, I tell you that mu is 0.2, okay? That's my coefficient of friction. And I tell you that the normal force or the weight is say 100 newtons. And I say, find my force friction. So the other thing that you can do to find your force friction is that you can take mu times force normal. Now, boom, boom, there you go, multiplied together. 3 ways you can calculate your force friction. Pull it, MA, mu times force normal, okay? And you're going to do all 3 of those in the course of this lab. So when you get to question number 9, how much force would be required to pull the block at a constant velocity? What are the 2 most important words on question number 9?
Constant velocity.
Constant velocity. What do all the forces add up to? 0. Keep that in mind. Okay, let's grab that camera. Let's go to the back. Let's talk about the rest of the lab.
Check this.
Yes,
Check
sir.
this, dude.
Why aren't I feeling one? Yeah, I'm tired. I wish I would.
Vitor, kind of get it where you make kind of like almost like the top of this. With
Yeah,
this
hold
kind
it
of,
up.
Hold it.
Yeah, you just want me to hold it?
Yeah, that's fine. Okay, so here's the second part of the lab. And this is going to deal with what we call static equilibrium, right? So this is a table, and we use it to measure forces, so it's cleverly called a force table, okay? Not the best marketing technique in the world, but you get the point. So you can do 2 things to each string. You can loosen this, and you can change the angle, okay? That's one thing that you can do. And you can also change how much weight that you hang from the end of the string. So basically the easiest way to view this is that it's like a 3-way tug of war. So you have one vector pulling this way, and that's balancing out the effect of the other 2. This one's balancing out those 2, this one's balancing out those 2. It's a 3-way tug of war. So what you want to do is get it to a point of equilibrium where this ring stays right in the middle of that metal stop. So when I let go of it, notice it begins to accelerate, okay? Which means this thing is not in equilibrium. So again, I can either change the angle, so a little bit. So if I do that, now when I let go of it, it stays. So those are what you can do. So what you want to do is you want to keep one vector at 0 degrees. Don't change that one. You can change the weights on it, but keep that one at 0. So what we're going to do is we're going to do like we've done with all the vectors. We're going to make 0 the positive x-axis. You're going to measure around like this, and we're going to call this vector B. So with mine, that would be like 99 degrees. And then I'm going to go all the way around to here, and this one's going to be like at 243 degrees, okay? So those are going to be my angles. So to get the value of the forces, once you get everything set up, so what's creating this tension is gravity pulling down on these weights. After you get it set up, then you're just going to take these weights off, like this is 20 grams. So you're going to add up the total weight on the end of each string, multiply that by, convert that to kilograms, multiply it by 9.8, boom, there's your forces. So here's what you want to visualize. So you've got vector A going like this. You have vector B pulling like this, if I draw this tip to tail, okay? So vector B is going like this. Now, vector C is pulling this way, back like this. So if I were to draw this A, B, C, where do you think I should theoretically end up?
0, 0.
Back at that origin. So, because if you think about it, if you were to just look at the resultant of B and C, so if I have vector B, and then I draw vector C like this, and draw that resultant's going to be coming out here like this, which should be just the opposite of A. So B is balancing out A and C. That's why I said this is like a three-way tug of war. What I don't want three equal weights and each angle being 120 degrees, okay? That's not the point of the story, okay? I want 3 different weights, I want 3 different angles. When you get it right, if you give it a little bit of tap, it should stay right there in place. Okay, got that one. Good, got it? Okay. Here's the third part. I know we're not going to get down to this today. Here's going to be the third part. With this one, this is going to be this part over here where you've got the accelerated motion with a constant mass. So you're going to take your cart and you're going to weigh it. And then you're going to find the mass. So what's the easiest way to weigh the cart?
With the
Newton meter.
Yeah, take your Newton scale, hold it up. Make sure though that it's hanging freely, and make sure that that isn't part of this catching on the side of the spring or of the scale. Otherwise, you're going to get a false reading. So once you know the weight, how can you find the mass?
Multiply times.
Nope.
Divide.
By
gravity.
Acceleration.
9.8 meters per second squared.
which is the acceleration caused by gravity.
Come on, Luke.
Divide by gravity. Let's think this through
The
for
value.
just a second.
Yeah.
You can cut say, yeah, okay. Now, so what you're going to do is that you need a 10-gram mass, which is a cute little thing like this, okay? You're going to need 20-gram mass, and you're going to need a 500-gram mass, okay? So you're going to put 500-gram mass up here. You're going to put 20-gram mass up here, and then you're going to take the 10-gram mass and make sure that this thing can travel freely. And can you hook that on the end of that string?
Oh my god.
Okay. Now, when I let go of it, what's going to happen?
It's going to accelerate.
It's going to accelerate. Okay? Ooh, fancy. Now, did it accelerate very much?
No.
No. But what we're going to do is we're going to calculate this acceleration. Now, when I let go of it, what's the only force acting to make this thing move?
Gravity.
Acting on what?
The weight.
The 10-gram mass, right? Now, somebody have a calculator?
Yes,
Okay, good.
Okay, so take 10 grams, divide that by 1,000, then multiply that by the acceleration due to gravity, 9.8 meters per second squared. What do you get?
0.098.
0.098. So what we're going to assume is that 0.098 newtons of force is acting on this entire mass. Now, think about this. If I just cut the string, what's going to be the acceleration of that 0.098 Newton mass?
-9.
Why?
Because gravity.
Okay?
And it's the, it doesn't have the normal force on the string.
Yeah, there's no upward tension, right, dragging this. So this is like you're ready to go out to prom. Okay, you got date, you paid for everything. You're ready to go, right? And you're ready to walk out the door, and mom and dad goes, hey, by the way, you need to take along your little brother and sister. It's like, really? Seriously? So you've got to drag them with you. So what's going to happen to your acceleration? It's going to go down. Because you still have the same desire, 0.098 newtons, but now you've got to drag your brother and sister with you. It's like, oh, seriously? So here's the deal. So what we're going to initially assume is that this is a frictionless surface. So over here on page 3, it's going to say force net. And I'll write this up on the board. So that force net is what we're going to assume is there's no frictional mafia, there's no gravity mafia, nothing to overcome. We're assuming that that 0.098 newtons is available to drag this entire thing. Now, here's what I want you to think through. If I cut the string, there's still only 0.098 newtons of force available. But that force is only going to act on the 10 grams. So I promise you, if you take that 0.098 newtons and divide it back by the mass, you're going to get 9.8 meters per second squared. So when you get into a situation like this, and you're going to use force equals ma, there's your force. Listen to me, listen to me, listen to me, listen to me, listen to me. The mass that you're going to use is the entire mass of the system. The 10 grams that are on the end, the 20, the 500, and the cart itself. Okay? Because what people tend to do is they don't add in the 10 grams. They think, well, that's part of the weight. But gravity is making that accelerate as well. Okay? So when you're going to use F equals ma, and you are, okay, you're going to take the weight of what's ever on the end of the string, and you're going to divide it by the combined mass of the entire system. The 10, the 20, the 500. Now, swap me out. Give me back that 10 and put that 20 on the end. Okay, now what do you think is going to happen to the acceleration?
It's gonna increase
It's going to increase. Why?
because there's more mass that's pulling down on the cart and less mass that's being dragged.
Okay? Now, why do you think I put that 10 gram mass back up here?
Because it was still part of the system.
Bingo. I want the total mass to remain the constant. Okay? I'm going to change the distribution of the mass, but I want the entire mass of the system to remain constant. So what you're going to do, and you'll see why this in just a second. I don't care what marks that you use, but you want to let this thing go 50 centimeters. Okay? You can go from, I don't care where you go. You can go, just make sure that it has like enough room to fall where it travels 50 centimeters that the weight doesn't hit the ground. Okay? So you're going to be maybe like, you're going to go from 40, let's say 30 here to 80. Okay? You want to have a couple people timing it and then compare those times. You're going to do 5 trials, take the average time. Got it? Good? Rand? Back we go.
Just leave it back. What's that for, bro?
Bro, you gotta score some.
Wait, didn't you scoring.
Okay. So,
I heard tornado before.
here's the deal.
What?
On page 3 with the cart,
Because I live close enough to it.
your net force is gonna be the weight of whatever is hanging from the string. So on that first one, you had 10 grams. So we're going to assume that that's the only force available to accelerate this system. So we did that, Madwood, to get 0.098.
Yep.
Okay? 0.098 newtons. So on page 3, we're on that 10 gram mass, where it says that net force, that's just gonna be the 10 grams times 9.8 meters per second squared, 0.098 newtons, okay? Then, with the 20 grams, the only thing that's gonna change is you're gonna take 20 grams times 9.8 meters per second squared. Oddly enough, you're gonna get double the amount of force. So, typically, on your total accelerated mass, that should be around 1 kilogram. Okay, so kind of about halfway down on page 3, when you add the 10 gram, the 20 gram, the 500 gram, and the mass of the cart itself, that should be around 1 kilogram. Okay, that's an ish, but it should be something pretty close to that. Now, when you get to that one where it says for each trial, determine the final velocity of the cart using the experimental acceleration and the average time. So what you're going to do is that you are going to calculate a theoretical acceleration, okay, based upon taking the net force, which in this case would be 0.098 newtons, and dividing it by the total mass. So this is going to get you your theoretical acceleration, okay? So you're going to take, on that first trial, you're going to take 0.098 newtons, and you're going to divide that by the total mass. That's going to get you your theoretical acceleration, assuming that it's a frictionless surface. Now, you're also going to calculate an experimental acceleration. So this is where you have to use your distances. So on that experimental, here's what we're going to do. We're going to take advantage of the idea that distance equals 1/2 AT squared plus V naught time. Now, if we're clever, and we are, what are we going to let the initial velocity of the cart be?
0.
0. That's going to go away. We don't have to worry about that. Now, you're going to know how far you traveled, right?
Yeah.
You're going to know that number. You're going to know an average time. Okay? So this is why you want to let the distance be 0.5 meters, because then you take 2x divided by t squared to get your acceleration. Well, if 2 is 1/2 meter, or 2 times 1/2 meter divided by t squared, all you have to do is say, just mathematically, it's just the inverse of t squared. Okay? So there's nothing magic about 0.5 meters, but it makes the math side of the calculations work out better. Now, whoa,
Is that a
good
marble?
catch. So, the other thing, you want to make sure that the cart is still moving when it crosses the 50 centimeter mark. Don't stop it and stop the timing at the same time, because then you're like stopping it. You want it to be moving when it crosses that 50 centimeter mark, and then stop the stopwatch, okay? So, I am done. You've got the rest of the time to go through, focus on getting the data, okay? Focus on getting the data.
Yeah.